Let's throw up the answer key for those guys who are not here. Virtual kiddos. And yeah, if you guys are ever gone from school, know that this is online every single day. So most of you do not need to rewatch a video of our lesson because you were here. But if you're ever gone, like unexpectedly, or you know you're gonna be gone, know that I upload this right after class. So the answer key will be on there, then the notes will be on there, me explaining it. So kind of getting this class, but you can pause me or fast forward me as needed. And that's up online after school or after class. So if you ever had to be gone, just know that that's the case. That's out there for you. It's posted for the virtual kids, but at the same time, if you're home at all, I know some of my students in Algebra 2 had to be home the last couple of weeks because of just symptoms, and that it was online for them. They kind of just were able to transfer over to that. So, all right, so what I wanted to do is show you guys how this looks in geometry. So like how can we take a proof like we were doing last class with algebra and kind of make it a geometry proof? So if you guys could, yeah, look at that last example. So I think it was example 3 on our notes from last time. Pull that up quick. We're going to talk about how to make that kind of work here. And just so you guys know, we have about 2 more days of new notes, and then we'll review and test. So that would take us Monday, Tuesday, Wednesday review, Thursday test at the earliest. Kind of barring anything crazy happening, but so yeah, that's kind of what I'm shooting for is a Thursday test maybe. If we'll kind of see how things go though. So again, we're looking back at the 2-5 notes again. And flipping to the very last part of them. So this one. So I want to show you guys how we can include, basically take a geometry proof and make it into an algebra proof. And once you guys see this, it's just kind of a few extra steps to get us to that point. So if you look at this, this looks like a whole bunch of gibberish if you didn't know geometry before. So it tells us that angle FGJ, so FGJ, this one, is congruent to JGK, which is this one. They tell us that information here. Then they tell us that JGK, the one I just marked, is congruent to KGH. Is that one. So I have to write that down as a given statement. I can't make any conclusions quite yet. I know some of you guys are like kind of chomping at the bit to say what you know about that because there's kind of something pretty obvious that flows from there, but we have to write that down as our given statement. Now, all the different letters are kind of annoying, so I'm going to shorten this up a bit here. Hopefully you'll like this. I'm just going to call this angles 1, 2, and 3. So 1 equals 2, 2 equals 3. I think that makes it a lot easier. I'll try to do this on proofs on tests. So angle 1 equals 2, and angle 2 equals 3. That's given to us. It's a lot better than having to write 3 letters every time. I feel like we're speaking in gibberish. Does everyone see what I did there? I just replaced those names with angles 1, 2, and 3. And like I said, on a test, I'll typically try to do that just for ease of, part of it is my grading too, is just for me to have to like check what angle you're talking about. It's a lot easier to do. They also give us information that angle 1 equals 6 6x plus 7, and then this would be angle 3 equals 8x minus 5. I might put that right away in this first step of the proof because it's still given. So that's given to us. So someone told us that information. We did not know that all on our own. Now they tell us we're trying to prove x equals 6. Obviously, we wouldn't have known that unless they told us that, or if we actually did the work. So we're trying to connect those dots and make that work. Anyone have an idea of something you can conclude based off that given statement now? This is kind of the thing I was trying to say, hang on, wait, like kind of hold your horses, like, what can we conclude about that first given statement? Yeah. Yeah, if 1 equals 2 and 2 equals 3, then we can say that 1 equals 3. That's gonna be our step 2. And you guys might want to flip your sheet over and look at the rules, the reason why that would be. Does anyone know the reason? How can you say that? I mean, so Luke's right, 1 equals 3, but how does he know that? We can't just say because, the obvious theorem, that's not a theorem. Duh is not an option. What's the reason? Yeah. You could use transitive or substitution I'd be okay with. So like I said, transitive is one of those a lot of times, it should have an it in there. Am I spelling it right? Okay. Oh, there is only one T. So if you called it substitution, that would also be okay. This is probably more technically transitive because that 2 is that double, like when you're mentioning something twice. So 1 equals 3 by transitive. All right, that doesn't really get us anywhere. That doesn't tell us that x equals 6. That helps. Any thoughts on what we can do next then? How can we get to the fact that x equals 6? If I know 1 equals 3, what can we do? Yep.
But 6x plus 7 equals 8x minus 5.
Yeah, so we can say that these two have to be equal. 6x plus 7 has to equal 8x minus 5. And we just replace something. So in math, when we replace something, what do we call that? Substitution, yep, so substitution there. So in this case, I would call this one substitution. I think transitive, I want to spell it like I spell substitution. All right, now it's starting to look like algebra. So now those first 2 steps, like that's kind of the new stuff for us. The rest of it is just the algebra we did in last class. Trying to get the x equal to 6. So now we're going to do the math that is required to get ourselves to that point. What do you guys want to do next? What should we do?
Add 5.
You want to add 5? That's fine. We can add 5. So since we're adding, obviously it's addition property. So we get 6x plus 12 equals 8x. And that's what Peyton suggested. That's fine. So he did addition. Now if someone's like, I wouldn't have done that, then you should have spoke up. He's the only one who answered me, so I'm going with what he says. And that works fine. Once we have addition there, what do we need to do next? Now it's not really an option. What to do? Those x's together, right? So which x do we need to move? Yeah, that 6x has got to move over, so because that other one's all alone already. So this will cancel, so I'll get 12 equals 2x by subtraction. And don't abbreviate subtraction too small. Subtract is fine. And then we still need 2 more steps. And as much as you want to skip over one of those steps, you can't just flip this because you feel like it. If you want to flip it, the equation, you have to give that step. But we're going to divide by 2 first. So 6 will equal x. So again, that's division. And then we flip that around. And I always get these two mixed up. That one's called, it's the symmetric one where you can flip it. So that's kind of the start of what we're going to be doing now with kind of taking the algebra and making it into the geometry piece of it. The algebra, I think, is just so much easier for us to kind of comprehend because we're good at, I mean, we've done algebra. You guys are here because you passed algebra, I hope. You know, you got through that part. So these steps are kind of more intuitive for you guys. The geometry piece of it is going to be some learning. So hopefully we'll get you guys there. I'm going to do some more proofs with these today, try to get you guys more comfortable with that. Pass out our new notes for today, which are going to look really similar to the last ones. Yeah, if you guys want to throw those back in a binder or something like that, Izzy, I'll send it back with James group here. Yeah, that's great. So you want to go down to the nurse and so stop in the main office and just tell them what you're, so they, yeah. Yes, let me flip over to notes for this. It was kind of our warm-up question there, so. All right, so now we're getting into like more proofs based off of geometry. Now I'll tell you guys, we'll do that this chapter, and then we are going to come back to proofs a little bit later in a different chapter. But for the most part, what we're working on in these is just kind of connecting that geometry with the algebra pieces of it. But always feel free to stop me if something's not making sense. We're kind of using the new rules we've been using so far and not adding too many more new ones here. Oops, this is the 21st. Second. So what this first chart's trying to show you, and I showed you guys kind of basically we kind of did like the left half of this chart last time. So that AB equals AB, that was reflexive property. Basically the same rule that would apply to algebra applies to geometry, or the same thing that applies to segments would apply to angles. So kind of all the different things we can do in algebra, we can still do in geometry with the same reasons. So same thing with addition and subtraction and multiplication, division, do the same thing. So all properties of equality so all the properties we learned so far. They also apply to segments and angles. Now, there's something our book uses, and some geometry teachers are super picky about this, and as much as you might want to disagree, I don't consider myself to be a super picky geometry teacher. I'm the only one you've had, so you probably don't know how to compare me. But I'm not picky about a few different things that the book will use. So if you notice, they have this little M, angle 1, and then that's like the little equal sign with the squiggle on the top. Just to save us time and kind of energy and like just frustration, I just automatically call that angle 1 equals angle 1. I'm not gonna like, and technically, that doesn't exactly mean the exact same thing, but there's these slight little differences that I just don't think we need to get into. If you're telling me the measure of angle 1 is congruent to the measure of angle 1, that's fine. Angle 1 equals angle 1, same thing. So if you look at our book, I don't want you to get confused and say, what is that little M there? This is just a kind of fancier or more technical way to write this. And I think this is just easier, so let's stick with the more straightforward. Another thing our book is like, we'll do sometimes is kind of what you see here, is they're talking about segments. So they have AB kind of italicized is congruent to AB. And again, I'm just gonna write this maybe as AB equals AB. And again, the book is a little bit different on that, and some teachers are a little bit different on that, that there's a slight difference in that notation, but I kind of consider them to be one and the same. So just know that I'm not gonna be picky about that, so if you see that in the book, and if you see, sometimes the book will even do 2 different steps with these, and I just consider that to be one thing. So I hope that makes sense. It's kind of a just a notation thing. So I'll use the more basic version typically. If you want to put the little M in, that's up to you, but you don't need to. So I'm going to talk to you guys about different rules we can use in proofs. So the word postulate is just a really fancy word for a rule. And definitions, again, same idea. It's just, again, technical words in geometry, postulate versus a theorem versus a definition. So a postulate is something we can use in proofs. Some postulates we can use in proofs. So I'm gonna show you what it looks like, and I'm gonna show you what we would call it, and then kind of just show you an example of that. So, so typically we have our statement, and then we have our reason in a 2-column proof. Now, I'm not actually making a 2-column proof right now. I'm just showing you how this will look. And so I'm also going to draw a little diagram here for you. So you can kind of see what it looks like if it was in a proof where we were trying to use it. Let me show you guys what we have going on here. So if you guys want to draw, I'm going to draw an angle, and then I'm going to cut it kind of in half here, hopefully. So the big angle is ABC. The 2 little angles are angles 1 and 2. Make sure you're writing this down, please. There's no reason to have your calculator out right now. So you guys can draw that diagram. So if you see something like that and you're stuck in a proof, it's a really good idea. So we're going to break this up. So hopefully you have a little bit more space. Sorry if I didn't leave you that ahead of time. You can always write things down below or up above. So anything you guys can kind of conclude about this drawing, just based on looking at it. And it's kind of an obvious thing where you're like, really, you would say that? What do you know about angle 1 and 2 together? What do they do? Yeah, so angles 1 and 2 together, if I put them together, they equal angle ABC. And again, you might say, well, that seems really obvious. There's things we have to see in geometry that seem really obvious, but you have to state that anyhow. So what do you think our reason would be? What are we doing there? What are we doing with those angles? What math are we doing? What's it?
Addition.
Addition. So the reason is called angle addition. Like, I mean, we're getting really creative here with our names. Angle addition property. So just like I could add, I could add numbers together, I could add variables, I can do the same thing with angles. So angle addition property is the reason I'm able to say that 1 + 2 equals the bigger angle. So that's going to be something we're going to use in proofs quite a bit. So be able to add those angles together. We can do the same thing with segments. So hopefully you have a little bit of space. If you don't, you can maybe write it above. This one's just a segment, so it's not as big of a drawing. Well, let's use different letters, sorry. So let's use D, E, and F. So just like we did for angle addition, we can also do segment addition. Also do segment addition there. So tell me how I would write that statement. What would the segment addition statement be? So it's going to be 2 segments add up to a third. How could I write that? Give me one of the smaller segments. This drawing, that's one of the smaller ones. Yeah.
DE plus EF equals BF.
Yeah. So DE plus EF equals DF. Now again, I usually draw little segment lines over the top, show their segments. Again, you might see the book doesn't do that, and you're like, oh, why don't they do that? And again, it's just that weird little notation thing that they don't do that. So what Michael just said was this segment and the even shorter one together will add up to the bigger statement. Seems pretty straightforward, I think. So that's just called segment addition. So if I'm trying to find out something about a bigger segment, I would use that. We're gonna do one more rule, and then we'll take a little break, and then we'll actually see these in some proofs. So the next one is a definition to use in a proof. And again, you don't need to know, I'm not gonna say, hey, is this a definition or a postulate? I don't really care if you know that or not. To be honest, I don't know that I would be able to make a complete list of which ones are definitions and which ones are postulates. But again, it's something I can use in a proof. And again, I'll give you guys another little drawing, statement, reason, and then the diagram. So in this drawing, in this specific drawing, they tell us M is the midpoint. But I also in parentheses wrote it could be a segment or angle bisector. So obviously in this drawing, it's not an angle bisector because we're not talking about an angle. But I'm trying to show you guys that this is another rule that we could use a definition for in a proof. So if they gave you as a midpoint, if they told you it was a segment bisector or angle bisector, then we're going to be able to make a conclusion about this drawing. So if I know M is a midpoint, what do I know? If I know M is a midpoint, what do I know about this segment or these little segments? Yeah, Michael?
they're equal,
Yeah, so what equals what?
GM equals MH.
So GM equals MH. And the reason for that would be definition of a midpoint. I'm okay if you just saying it's a midpoint. And again, in another circumstance, you might say, oh, it's a segment bisector. That's what was given to you. It's just the reason we're able to do that. Or an angle bisector. So we'll use that as our reason. So again, you don't have to write, it's because it's a definition, you're just telling you what you know about it. And we'll see that we'll see that in some different proofs that we'll look at today. So it's damp in the grass, but we could probably go outside and do maybe a quick would you rather or something like that. If that's okay, if you guys want to go outside. I think we actually have good weather again this week, though. I feel like sometimes you guys kind of get the short end of the stick because the grass is so wet. Typically, we do whiteboards in a lot of my classes, and I don't want you guys having to sit in the grass and standing and doing whiteboards isn't exactly easy to do. So we can go outside. Like I said, we'll just do some would you rather. You guys can mingle out there a little bit, take a little mask break. And we'll come back in here in a little bit then too. So, yes, and guys in this side of the room head up first. Next couple rows. Online, we're gonna pause you guys and then we'll come back. Next two guys.